Here is the jump to subroutine instruction. It provides linkage. It was very fast linkage for its day. It does a number of things automatically. The instruction, it's JSR, and there is the opcode pattern, one of the unique opcode patterns remaining. You specify a register. This is a linkage register. And you specify a destination. The destination is specified as a mode and a register, the usual form of addressing. It tells you where you're going to, where the subroutine is. This is the destination. This is the subroutine you're calling. What happens? Well, whatever gets calculated for the destination is put into an internal temporary register. It's held. The value that's in this register, bits 8 through 6, the R's here, is put onto the stack. It's that should be an & sign, I think. It's put onto the stack, and the stack pointer is decremented, meaning you've pushed something onto the stack. So the contents of this register are pushed onto the stack. Then the program counter, which has been updated, it's pointing at the instruction immediately following the JSR. Program counters are always updated. It's pointing at the instruction after. That's presumably the return point. That's where you're going to come back. So it pushes into this register designated with the R's here, the contents of the program counter, which is updated and is pointing at the return point. And then it takes the value of the destination here that it was holding in a temporary internal register that you can't see, and it puts it into the PC. Well, the act of putting it into the PC, of course, causes the next instruction to be fetched from there. And there is the first instruction, presumably, of the subroutine. So it does several things. It pushes contents onto the stack, and it branches puts the contents of some register onto the stack so you can recover it later. It puts the program counter into that register so you can use it to return later. And it puts the destination into the PC, thereby causing the subroutine to start to execute. Get that? This is a key point here, is the idea that you are putting the program counter into the linkage register. This is it saves the linkage register and puts the program counter into it. So that when you're down the subroutine, if you want to make a return, all you have to do is use the contents of this register if you haven't clobbered them. Normally, if it's a big program and you need the register, you'll save it and restore it later. But this is your path back to the calling program. Okay, here is the return from subroutine instruction. It kind of reverses the procedure for the subroutine call instruction, JSR. This is the opcode. You're running out of space for these opcodes, but it's one giant long number. That pattern is unique, and it specifies the opcode in question. This, again, is the PDP-11 40 manual. And you have specify a register. No mode, just a register. What happens is it takes the contents of the register and puts it into the program counter. Then it takes the contents pointed to by the stack pointer and puts them into the register and increments the stack pointer. In other words, it pops the top value off the stack and puts it into the register. And that's it. You're home. Presuming that when you came down from the JSR, that this is the same register, and that's the register that contains the value from the program counter in the calling routine, which tells you where to return from. So basically, it uses that value, puts it into the PC, and then restores the value, which, if you recall, it saved it earlier, and it saved it on the stack. Now, this mechanism of subroutine calling is fairly, it doesn't save any registers except the linkage register. But you can go into a subroutine with one instruction, execute a subroutine, come out with one instruction. This was vastly different than the IBM mainframe of the day, where linkage into a subroutine was a fairly extensive process involving, well, they saved all the registers, and they had 16 registers. But the linkage situation was not done in hardware. It was done with instructions, and it was time-consuming. So subroutines relatively speaking, were expensive in the architecture of the mainframe, but with the PDP-11 we got very fast subroutine calling. And this, of course, made the machine ideal for handling real-time events, where you had to jump into a subroutine or some kind of a procedure to handle an incoming piece of data quickly and get back out quickly. This was part of it. There's also the same mechanism is used when there's a trap or an interrupt. When the device signals that it needs attention, or you need to switch to the operating system for some operating system provided service, the same basic procedure is used for linkage. It's comparable, but this is the JSR and RTS instructions. Interrupts on the PDP-11 are handled in a priority fashion. Each device has a priority, and it can request interrupt service from the machine. If the machine is operating at a lower priority level than the interrupting device, the interrupt goes through. When an interrupt comes in, the device sends an address. The address is the address of what's called an interrupt vector. These are two 16-bit words in low kernel address space. They're in low memory. It says normally physical memory, between 0 and 776 and be octal. The first word of the interrupt vector contains the address of the interrupt service routine, the piece of software which is going to handle the interrupt. The second address is the address that will be loaded into the processor status word, all of the various bits and so forth that you want to start off with on entry into the service routine. So what happens is the processor, whatever it's doing, it stops. It gets this vector address. It goes there. It stores the current value of the program counter and the processor status word in the stack. It then takes the address from low memory of the routine that it's going to enter, puts that in the program counter, and loads the processor status word with the next word, which is the settings that need to be handled, and you're off to the races. Because the next thing it executes is the first instruction in the interrupt service routine. It interrupted. It remembered where it was. It put the current value of the program counter and the PSW onto the stack so we can restore them later. And we loaded a new program counter and a new PSW. And by loading a new program counter, the next thing it does is going to execute the instruction pointed to by the program counter, which is in the interrupt service routine. Now, the interrupt service routine will probably store the other registers. I don't know. It'll do something. And when it's done, the process is more or less reversed. The stack elements containing the original processor status word and the program counter are restored. And by restoring them, you're back where you were when the interrupt took place. So it's a relatively simple procedure. Each device has its own interrupt service routine. It has its own set of vector in low memory. And it's relatively foolproof. It is a priority-based system in that each device has a priority on the bus, and if a higher priority routine is running, the lower priority interrupts wait. They pend. Obviously, high-speed devices get higher priority. Low-speed devices get lower priority.